Okay, so let us resume with our third lecture. And let's start recalling that in the previous lecture, we started with our analysis of the Gauss-Kodatzy constraint equations in the case where they are decoupled. In particular, this involved a CMC condition. We obtained at the end of the last lecture some uniqueness results associated with the vacuum the vacuum system in this case. And in this case, the core of the analysis relied on the associated generics equation that in vacuum was given by this. Recalling that here, basically, this coefficient is given by the traceless part associated with extrinsic curvature. And that this coefficient is basically given by the square of the mean curvature. Okay. And also in the last lecture, we presented the monotone iteration scheme in the case of closed manifolds. That is the main tool that we are going to use in order to deal with generics type equations. And the main conclusion was that the core of the analysis gets reduced to that of constructing appropriate super solutions associated with this kind of equations. And this is what we are going to start doing now. So the idea is to focus again on the vacuum case where we have to deal with this equation, and the case where we incorporate some physical sources that allow for us to decouple the equations. This is treated in the lecture notes. And we are going to provide certain constructions for super solutions that are going to allow us to classify, in particular, the vacuum case under a CMC condition completely for in the case of closed manifolds. And these results go back to this pioneering work by Jim Eisenberg, where this classification was obtained in the case of smooth solutions. And adaptations to low regularity settings have been developed through these years. In particular, we're going to follow this paper by David Maxwell. We're going to follow this quite closely. And so let us start with this analysis now. Then the first result that we will present is this construction for Yamabe non-negative solutions. Okay, so if we are in a closed manifold of the level of regularity that we have been dealing with, we are Yamabe non-negative, and we assume we want to find solutions via the monotone iteration scheme, so we have to produce barriers. Then our equation above, associated with the vacuum generics equation, admits a solution if and only if one of these three conditions is satisfied. Okay, so here we have both necessary and sufficient conditions. And here it's important for us to highlight the fact that we are not assuming that the mean curvature has to be constant in this case, okay? And well, let us go through this proof in quite some detail. We will do this in this lemma, and then in other constructions, in particular for the Yamabe negative case, we will just sketch the proofs since they rely on the same kind of analytic tools and constructions. And so let us start considering the backwards implication. So we assume that these conditions hold, and we want to show that we have solutions via the construction of barriers. Let us first notice that this case, the first one, is quite trivial, because in this case, if both the coefficients ATT and A2O vanish here in the right-hand side, then we have that this equation gets transformed into this one. And one can see that this is actually the Yamabe equation for a conformal deformation to zero scalar curvature. And therefore, what we are saying is that if we are Yamabe zero, then this has a positive solution. And this is due to our classification on low regularity Yamabe that we presented in the previous lecture. So this case follows trivially, and we have to focus on the second and third cases. So in these cases, in both cases, the coefficient ATT is not going to be identically zero. We have to recall that both coefficients are non-negative. Okay. And here the strategy is to exploit the Yamabe classification in order to fix properties of the scalar curvature. and also to appeal to conformal covariance, to find a suitable conformal elements in our conformal class where things get simplified. So let us start first considering a conformal deformation to a metric gamma 1 that fixes the sign of the scalar curvature according to the sign of the Yamabe invariant. This was something that is guaranteed from the Yamabe classification. And therefore, we can appeal to conformal covariance to say that our equation, the original equation, has a solution if and only if this associated Lichtenberg's equation, this conformally related Lichtenberg's equation, has a positive solution. Okay, well now this coefficient, the coefficient ATT, has to transform in this way with phi 1. So we're going to, the important thing about this equation is that now we control the sign of the scalar curvature here. We know that this is non-negative. And therefore that allows us to guarantee that this combination of the scalar curvature and the mean curvature is non-negative and not identically zero. And this is can be extracted from these two conditions, since if we are in the Yamabe positive case, then our first conformal deformation gave us a metric with positive scalar curvature, and then the sum of this plus the mean curvature is going to be positive. And if we are in the third case, this is non-negative and not exactly zero. So again, the combination of the scalar curvature and the mean curvature is going to satisfy these two inequalities, this inequality and this property. And then we can appeal to the mapping properties associated with the Poisson operator that we saw in the last lecture, in particular since we have just established this condition together with this one here. We know that the operator here in the left-hand side is an isomorphism. And so we can find a solution to this equation, in particular if this is non-negative and not vanishing, again, through our hypothesis here. We can appeal to the maximum principle to show that the unique solution to this equation is actually strictly positive. So it is a good conformal factor with which we can appeal to a second conformal deformation. And again, we can use conformal covariance to say that this equation 86 is going to admit a positive solution if and only if the conformally related equation 88 admits a positive solution. Or now, again, this ATT2 scales in this form with phi 2. And furthermore, now the important thing is that the scalar curvature associated with gamma 2 via the well-known conformal transformations associated to scalar curvature is given by this expression. But this can be substituted from the definition of phi 2 here. Okay, so this shows that the right-hand side of this equation is going to be given in terms of A2 and ATT1. But then using this relation between ATT1 and ATT2, one gets this exponent for phi 2. Okay, so now this expression for the scalar curvature associated with gamma 2 can be substituted here. And now we see that the coefficients on both sides are the same, given in terms of ATT2 and A2. And this equation now is amenable to analysis of constant sub and super solutions. So for instance, if we look for a constant barrier, then this term is going to vanish. And since the coefficients on both sides are the same, we just have to compare the powers of the functions that appear with each coefficient. And this is what we are doing here. For instance, if we look for a constant super solution, this is the condition that was going to define a constant super solution. And in order to guarantee this, one can straightforwardly compare the coefficients and see that the super solution must satisfy these lower bounds, where phi 2 is a fixed continuous function, so everything here is well defined. And therefore, picking a sufficiently large positive constant, we can satisfy these two conditions, and we get a positive constant super solution for our equation 88. And one can do something quite similar in the case of subsolutions in order to find constant subsolutions. And basically here one is going to have an opposite inequality. and we have to change the maximums by minimum. And doing that, one finds that a constant subsolution must be bounded by above by these expressions. Again, since phi2 is a positive continuous function, this is going to be a positive number. And therefore, we can always find a constant positive subsolution. And these conditions also guarantee that the barriers are compatible in this sense. And therefore, we have provided appropriate barriers for the monotone iteration scheme associated with equation 88 in this case. And therefore, the monotone iteration scheme guarantees the existence of a positive solution, and conformal covariance then guarantees that the original equation admits a positive solution under our hypothesis. So let us now prove the necessity of conditions 1 to 3. And in fact, the necessity conditions 1 to 3 is equivalent to showing that these two conditions here are valid. And one can see this directly, since going back to our hypothesis, only in the first hypothesis we have that the traceless part of extrinsic curvature vanishes, and in the other two this is non-zero. And therefore, what one wants to show is that if this is true, then we must fall in the first case, which implies that the Yamaha invariant is zero and all the coefficients vanish. And in this case of vacuum, all the coefficients vanish implies merely that actually the mean curvature vanishes identically. Notice that if this implication holds, it implies that if this is true, then we fall into case 1. Now, if this is not true, then the traceless part of the extrinsic curvature is not identically zero. And the point is that if it also holds that the A-tau coefficient is zero, we want to show that this implies Yamaha positivity so as to fall into case 2. Because going again back to our hypothesis, if these two conditions hold, then we need to prove Yamaha positivity. This is what we are saying here. And notice that if this condition holds, then either the mean curvature is identically zero and is not identically zero, and in that case we are already in condition 3, or it is identically zero, and if then this statement is true, we fall into case 2. So we need to basically prove these two statements. And in order to do that, let us assume that we have a solution associated with our generics equation. Then we do the conformal transformation to the solution that solves the geometric problem. And therefore, appealing to the conformal transformation rules for scalar curvature, we have this identity. Then one uses the generics equation here to replace in the right-hand side things in terms of ATT and A-tau. Okay? Considering the first item here is ATT happens to be identically zero, then what we see is that this term would be zero in that case. And the equation gets reduced to saying that the scalar curvature of G is equal to A-tau, minus A-tau. And since A-tau is non-negative, this would be non-positive. And therefore, this would imply that the Yamaha invariant, since this is a conformal invariant, it can be computed with the metric G, is non-positive, this condition. But by hypothesis, we know that it is non-negative in this lemma, so it would have to be zero. Okay. But furthermore, if in this case, A-tau were to be somewhere positive, so it's not identically zero, then it means that the scalar curvature of G somewhere it's negative. And therefore, one can test the Yamaha quotient on constant functions and discover that it's going to be negative. And therefore, we would be in the case of Yamaha negativity, but this contradicts our hypothesis. So this cannot happen. This condition here under our hypothesis cannot happen. And therefore, A-tau must be zero. And this establishes the first claim. Now, let us assume that A-tau is zero. Now we want to deal with this condition. So A-tau is zero and ATT is not identically zero. And therefore, this equation tells us that the scalar curvature is non-negative and given by this expression. Now we are considering the case where this is 0. And we know from the IMPA classification that if the scalar curvature is non-negative, then we can only have the IMPA invariant equal to 0 if it is the scalar curvature is exactly 0. Okay, and therefore this would imply that can only be IMPA 0 if this is 0, and therefore ATT has to be 0, but exactly 0. But we are assuming in this case by hypothesis that ATT is not exactly 0. So this is the assumption that we are holding. So this cannot happen. Okay. And therefore we have proved that in this case we are IMPA positive. So since this condition is our assumption, we cannot have a scalar curvature exactly 0, and this cannot happen. So we are IMPA positive. And this finishes the proof. So we see that we have constructed barriers for this case of IMPA non-negative, and therefore we have the exact criteria of solutions for the vacuum case. Similar results hold, as we have said, in non-vacuum, and this is something that can be checked in the lecture notes. But for the IMPA negative case, we need to sharpen our IMPA classification first. And in particular, we need the following two results that are also due to David Maxwell. And the first one basically gives us the exact criteria that we need in order to solve this equation in the IMPA negative case. So if we are in a closed manifold with our regularity assumptions, IMPA negative, then our Legendre equation associated to the vacuum case admits a solution if and only if there is a conformal deformation that produces scalar curvature equal to minus A2. So this is the criteria. And let us just sketch the proof. First, the case where the trace left part of extrinsic curvature is identically vanishing is trivial, because in this case, as we see here, this equation gets translated into this equation. And from the conformal transformation properties of scalar curvature, one sees that this is exactly, finding a positive solution to this equation is exactly equivalent to saying that there is a conformal metric that has as its scalar curvature this function here. So this case is trivial, and one needs only focus on the case where ATT is not identically vanishing, and this case is analyzed also by producing barriers. And this follows the lines of the previous lemma when one uses conformal covariance properties in order to go to a preferred conformal element where things get simplified, and then one appeals to this same kind of constructions. And therefore we are going to just leave that to be checked in the lecture notes so that we can move forward. And therefore, now we have a criteria to be able to solve the equation in the IMPA negative case. And the following lemma tells us that in particular, if the mean curvature, in this case, the mean curvature squared, that gives A202, is strictly positive, so it's bigger than some positive constant, then we can satisfy this condition that was the necessary criteria to solve the Legendre equation in the IMPA negative case. Okay, so here we have an explicit condition that guarantees the existence of solutions. And here again, we shall only sketch the proof because it appeals to the same ideas. And one again starts by appealing to a conformal deformation that gives us control over the sign of the scalar curvature. So we have a strictly continuous negative scalar curvature. And then one analyzes existence of solutions for the corresponding equation, that in this case is this one here. For this associated conformal equation. Since if we can find a conformal transformation from gamma 1 to constants to a scalar curvature equal to minus A2, then the composition of this conformal transformation with this second conformal transformation is going to produce the conformal transformation here that we're looking for. And in order to analyze equation 89, one appeals to this negativity property of the scalar curvature in order to produce barriers, and then one uses the monotone iteration scheme to guarantee the existence of a positive solution. And this follows again the lines of the first lemma, and the details can be consulted in the lecture notes and also in David Maxwell's paper. So the important thing now is that the two results above put together give us a precise characterization of solutions in the Yamabe negative case. So if the coefficient A2 is strictly positive, it is bigger than a constant that is positive, then the associated Lechonew's equation for vacuum admits a positive solution. Therefore, putting together everything that we have done above, we have this existence theorem that tells us that if we have a closed Riemannian manifold of our regularity and one considers the associated vacuum Lechonew's equation, then this equation admits a solution if one of the following four conditions are satisfied, and these first three conditions are the Yamabe non-negative cases that we saw in detail in the first lemma, and this arises via the last two results that we commented for Yamabe negative metrics. And in the case that the coefficient A2 is a constant, then these conditions are also necessary. Let us notice that the necessity condition for these first three cases doesn't need any kind of condition on the mean curvature being constant. And this was the content. We proved both implications in the case of the first lemma. So these are necessary and sufficient conditions regardless of whether 2 is a constant. But if it is a constant, this last condition also becomes a necessary condition for existence. The proof, we have already proven that these conditions guarantee existence and that these three conditions are also necessary. So the only thing that we need to worry about the proof, concerning the proof of this theorem, is the necessity of condition 4 under the hypothesis that A2 is a constant. Good, so let us assume that we are Yamabe negative, that A2 is a constant, and since this is a non-negative constant, it has to either be exactly 0 or strictly positive. What we want to show is that this condition of being exactly 0 is not allowed. So if we were to have A2 exactly 0 solving, and we have a solution to our equation, then again, if A2 is exactly 0, if we set this condition here, we get that our conformal factor solves this equation. But again, one can appeal to the conformal transformation of scalar curvature using this conformal factor, and one has this well-known rule by now, and one substitutes here the right-hand side into this expression, and one gets this expression here and this inequality. And this implies that the scalar curvature of this conformally related metric is actually non-negative. And this would imply that the Yamabe invariant associated with gamma has to be non-negative, but this contradicts our initial hypothesis of Yamabe negativity. Therefore, this cannot happen. And we must have this other case. And therefore, we have established the necessity. And as we said, it is important, and it will be important for us in the next lecture when dealing with far from CMC constructions, to notice that the conditions 1 to 3 don't need a CMC hypothesis. So with the aid of the above theorem, one can completely classify the vacuum CMC solutions. So if you're in vacuum and with a constant mean curvature condition, the momentum constraint reads as this equation. So basically X has to be a W2P conformal killing field. And therefore, since the traceless part of the extrinsic curvature is constructed using the conformal Lie derivative of this vector field, the solution of this equation, plus this TT part U. Since X is a conformal killing field, its conformal Lie derivative is 0, and this K tilde is going to equal our freely prescribed TT tensor. And therefore, the associated Lichtenberg's equation is going to read like 92. And here we have the classification just given above to state exactly when we have solutions. And this is compiled in this table. This table is well known from the work of James Eisenberg, as we said at the beginning, in the case of Moose metrics, and in the case of low regularity results and even rough solutions. This is well known also from the work of David Maxwell. So we have our classification on closed manifolds under CMC conditions. And now for us, the next step is going to be to try to analyze, again, the vacuum case, CMC condition, but on asymptotic Euclidean manifolds as an interesting model case of non-compact manifolds where we can analyze the Einstein Constraint equations. Therefore, now we start analyzing asymptotic Euclidean manifolds with some analytic preliminaries. The first thing, when we have to define our asymptotic Euclidean manifolds, and we will need to translate all the analytic machinery that we used above, mainly related to the mapping properties associated with the linear parts of our system, and certain properties associated with solid spaces and maximum principles, so that we can prove a monotone iteration scheme, and then we can use the maximum principles to construct barriers and so on. That's more or less the roadmap here, to translate these analytics into this case. And asymptotic Euclidean manifolds are very interesting because they are used to model isolated gravitational systems, such as an isolated star black hole or a few stars or black holes interacting among them. And these are non-compact manifolds which consist on a compact core and some finite number of ends, and the ends are diffeomorphic to the exterior of a closed ball in Rn. So this fixes the topological structure of our manifold. The topological picture would be something like this, where we have a compact core that may have non-trivial topology inside, but outside some compact set we have things that are diffeomorphic to the exterior of a ball in Rn. So this is a topological picture, and this is only fixing the topological picture. And manifolds with this topological structure are typically referred as Euclidean at infinity. So up to this point, we haven't imposed any kind of condition or restriction on the asymptotic geometry of our asymptotic Euclidean manifolds. And we will do this by first introducing certain weighted spaces that allow us to control the behavior of fields at infinity. And we shall demand that our metrics decay to the Euclidean metric at infinity at a certain rate. And for this, we first need to tailor our functional spaces to this setting. And this is also important so as to preserve good analytic properties of our elliptic operators. You can find all the details associated with these and part of the historical background in the lecture notes. And we just highlight that this analytic background has been established through very many notable contributions. For instance, this classical paper by Nirenberg and Walker, this paper by McOwens, Lockhart, Choquebrois, and Christodoulou, and also this classical paper by Robert Barnick. And in particular, we will follow the conventions of this paper. And therefore, let us introduce our weighted functional spaces, first on Rn. So let us consider a vector bundle over Rn, and we will define the weighted subvolume spaces WKP delta, where now we're introducing this new real parameter delta as the space of sections of our vector bundle, which are a subset of WKP log, satisfying that this norm is finite. Okay. Here, as we see, what we are doing is demanding that our sections and the first the derivatives up to order k belong to some weighted LP space where this sigma is given by this expression here. So we are demanding that they have to decay at infinity at a certain rate. And one can similarly define CK weighted spaces using the same kind of construction where this is the same function sigma. And again, these spaces control the behavior of fields at infinity in a very concrete way. And here we are using the parametrization for the weight parameter that was given by Robert Bartnik. And this has the advantage of giving us an heuristic estimates of the behavior of fields at infinity. In particular, what one realizes is that if one has this field that is in these weighted spaces, in case it's continuous, then near infinity it has to behave like this. So in particular, we see that if delta is negative, then fields have to decay at infinity. And all this can be made precise via sub-level embeddings associated with these weighted spaces. And all these properties are described and compiled in detail in the lecture notes. Now let us consider the case of a manifold that is Euclidean at infinity. So we have our topological structure and our manifold fixed. And it may have non-empty boundary, but in this case, we are going to assume that the boundary is contained in the compact core region. Okay, so in this setting, we see that we have a finite of n charts. These are basically the diffeomorphisms that enter into the definition of the manifold Euclidean at infinity. So the ends are diffeomorphic to the exterior of an open of a closed ball in Rn. So we have these diffeomorphisms that induce charts. And in the compact core, we can complete this into an open covering by coordinates systems by considering a finite number of coordinate systems covering the compact core. Then in order to extend our definition of functional spaces, this is now a standard procedure. One can appeal to a partition of unity subordinating to such a covering by these coordinate systems. Here we are letting this V sub A be equal to either Rn or the half space, depending on whether the charts, these charts covering the compact core are interior charts or boundary charts. And then if we have a vector bundle over M, we can define our weighted subgroup spaces as the subset of WKP log, such that this norm is finite. So here we are using the definitions given just above in the ends of the manifold, which are diffeomorphic to this exterior of a closed ball in Rn, and the usual subgroup spaces in the compact core of the manifold. Okay, so we have extended our functional spaces to these manifolds which are Euclidean at infinity. And what is important to realize is that these weighted spaces share most of the well-known properties for the usual subgroup spaces on bounded domains, that is the continuous and compact embedding properties, multiplication, interpolation, trace and extension properties associated with the boundary. Clearly, this is all under suitable hypotheses on the weight parameters, and the details there again are explained in the lecture notes. But well, now that we have this analytic machinery, we can control the behavior of fields at infinity by demanding that they belong to a suitable weighted space. And therefore we can define manifolds which are asymptotically Euclidean as Riemannian manifolds that satisfy these three properties. So the topological structure is fixed by demanding that they are Euclidean at infinity. Here we have a number of n charts. We are demanding that the metric is sufficiently regular so as to be continuous at least. And then that the difference between our Riemannian metric and the pullback of the Euclidean metric that we can put on Rn in the ends. So we use our asymptotic charge to pull back the Euclidean metric, that this difference belongs to a weighted space with delta negative. So as we said below, this implies that this difference has to decay to 0 at infinity, and therefore our Riemannian metric is decaying to the Euclidean metric at infinity, where this E is denoting the Euclidean metric on Rn. So this is our definition of asymptotic Euclidean manifold that captures all of the properties that we need. And now in this setting, we want to analyze the properties associated with the Poisson operator and the conformal killing Laplacian, but now acting on weighted spaces. And we know that this is important to translate all the machinery from closed manifolds to this setting. But before doing this, we will try to do this in the context of maps that involve boundary operators, so as to be able to incorporate black hole boundary conditions. And we saw in the first lecture that black hole boundary conditions can be naturally formulated in terms of initial data sets. And that's what we are going to do now, to try to rewrite such black hole boundary conditions within the setting of the conformal method, so that they provide boundary conditions for the Dictionary equation and the momentum constraint. Okay, and then we will present the mapping properties associated to the linear parts of the system, but also acting on the boundary. So recall that a manifold with compact boundary sigma, we have in this case we have a good characterization concerning what black hole initial conditions should look like, and these were given in terms of a convergence condition on the expansion coefficients, given by this condition here. And the expansion coefficients can be written in terms of the initial data set like this. And here we need to recall that this metric H is merely the restriction of our Riemannian metric G on our Cauchy surface to the boundary sigma, and that this small k represents the extrinsic curvature of sigma as an embedded hypersurface in the Cauchy surface M, with respect to the outward pointing chi unit normal nu. And now we want to rewrite these conditions in terms of our conformal data, okay? And here we are going to adopt first the following strategy. We can leave the negative expansion coefficient, this theta minus, as a free datum, prescribing it to be non-positive. Then one can manipulate this expression a little bit to see that this condition on theta plus can be rewritten in terms of theta minus. In fact, this implication holds. So these two black hole boundary conditions, which represent marginally trapped surfaces as boundary conditions, can be rewritten as this system of boundary conditions. Okay, and now one can introduce our conformal splittings for each of the quantities here, and it is just a computational exercise to rewrite these two equations like this. So this first equation is given by this equation here. And the second one gets translated into this boundary condition on the vector field X. So this works as a boundary condition for the generic equation. This works as a boundary condition for the momentum constraint. And here we have introduced some notation, in particular this nu hat now denotes the outward pointing unit normal vector field with respect to gamma, which is the fixed conformal datum. And H denotes the mean curvature of sigma as an embedded hypersurface, but now in M gamma. Okay, and it's in this case it's taken with respect to minus the normal. So it's explicitly given as the divergence in the metric gamma of the normal vector field according to gamma. So, well, these are now our conditions that capture this behavior on the expansion coefficients, where theta minus is a given free datum that is imposed to be non-positive. And now what we want to do now is to translate this inequality into some equality that we can use explicitly as a a boundary condition for the momentum constraint. And what we're going to do is to impose a link between these two parameters, which are free parameters of our problem. In particular, we're going to impose that this has to be non-negative. Okay. And this is what is done here in order to work with the boundary condition for X. One imposes this condition. And then one rewrites the boundary condition like this condition 100. And here notice that we have introduced this function V and imposed that this function V has to satisfy this inequality. So in particular, since this is non-negative, then one can directly see that this a priori bound guarantees that if this is satisfied, then this other inequality is also satisfied. But, and therefore, this other marginally trapped condition is going to be satisfied. But what is interesting to observe is that this condition that we are imposing is an a priori condition, and it stands as a constraint on the admissible solution if this solution is going to represent a marginally trapped surface satisfying this condition here. And so part of the PDE analysis related with this kind of boundary condition is related to showing that the solution that one obtains is a priori bounded by this function that one has to choose a priori. And therefore, well, under these conditions, one now has this system of boundary conditions for our constraint equations. This is going to be a boundary condition for the Chiroc's equation, the momentum constraint, and these are conditions a priori. Okay, this doesn't impose a restriction because it poses a link between two free parameters. And one important observation is that even if we are in the case of vacuum, where we may be able to decouple the Gauss and Kodazzi constraints as we did in the closed case, these boundary conditions would couple the equations through the boundary conditions. Let us highlight that X is involved in this K tilde, that we have an a priori bound here on phi that enters into this equation. So the equations can get coupled through the boundary conditions. So this would increase the difficulty in the analysis. But there is an interesting limiting case where one can actually achieve a complete decoupling of the boundary condition. And this is what we will do next. And notice that if we are thinking, for instance, about asymptotically Euclidean manifolds, and therefore we are going to impose certain decays for all the fields at infinity, and in particular, if we have some decay for the mean curvature, and if we impose a CMC condition to decouple the Gauss-Kodazzi constraints, then the CMC condition, together with the decay condition to 0 at infinity, is going to imply that the mean curvature has to be exactly 0. And in this case, we can pose boundary conditions that decouple as follows. If one thinks about an apparent horizon black hole condition that we defined in the first lecture to be a condition of this form, this condition is explicitly formulated using the definition of theta plus and replacing all the conformal data. It is explicitly reformulated as this condition 102. Furthermore, this condition, when one uses it in the theta minus expression, shows us that the theta minus expression is given in terms of the mean curvature of the boundary by this expression. And again, put together with the definition of theta minus, this implies that this mean curvature is given in terms of the extrinsic curvature on the normal direction. This extrinsic curvature of the Cauchy surface, computed on the normal direction to the boundary. And therefore, one here can see that this marginally trapped condition that one can use to complement this apparent horizon condition is actually equivalent to imposing this positivity condition on the mean curvature. This follows from this relation here. And from this relation here, this positivity condition is equivalent to this negativity condition on the extrinsic curvature. And if one replaces here the conformal data and one uses the fact that the mean curvature, we are assuming that is exactly 0, this is equivalent to this last condition, where now this is independent of the conformal factor. And therefore, one now can rewrite black hole boundary conditions in this way, where this arises as theta plus equal to 0, horizon condition, and this arises by demanding theta minus and a marginally trapped surface condition. Okay, so this is going to imply this marginally trapped surface condition. So what is important now is that this serves as a boundary condition for the Lichnow's equation, and this serves as a boundary condition for the momentum constraints, and these are completely decoupled, okay? And they correspond to this kind of black hole boundary conditions. So, as we were saying, we have the Lichnow's equation and the momentum constraint in vacuum, completely coupled with this marginally trapped surface and apparent horizon boundary conditions. Here, we should proceed as we did in the case of closed manifolds. First, one solves this equation that is completely coupled. One finds x. With this, one can construct this k tilde. Then all of the coefficients here are completely determined. And the core of the analysis relies in constructed solutions for the associated Lichnow's equation. And this pair of equations has been analyzed in detail by David Maxwell in this paper, and we shall present the main results in the following slides. Now, the idea is to analyze the mapping properties associated with the linear parts of our new boundary value problem. And the corresponding linear parts are going to be given by operators that have these forms. So now we have the Poisson operator, this kind of Neumann boundary condition. And we have this P2 is going to be the conformal Killing Laplacian with this also kind of Neumann boundary condition for X. We're assuming that our matrix is asymptotic Euclidean, so delta is negative here. A is an LP delta minus 2 function. B is a function on the boundary that has this level of regularity. And nu is the outward pointing normal to gamma. And here we need to translate all the tools that we developed in the case of closed manifolds to this case of asymptotic Euclidean manifolds. And we saw that the maximum principles were essential in our analysis, and so we're going to present them here. The interested reader can consult these proofs in the lecture notes and also in David Maxwell's paper that we referred above. But the ideas are basically quite similar to those of the closed case, but now one has to pay attention to the fact that the manifolds are non-compact and also to the boundary contributions. But what is important for us is that if one has here an asymptotic Euclidean manifold, and one considers a function that is W2P log that satisfies these inequalities. And now here one has to assume that A is non-negative as well as B, the boundary coefficient here is also non-negative. Then one can extract a sign for the solution of this inequality. And as we saw, this is important because we want to use this kind of maximum principles in the monotone iteration scheme in order to get solutions to linear problems that get trapped between barriers, and also because we want to prove positivity to certain equations when we construct the barriers. And in this context, we also saw that we needed the strong maximum principle, and so in the same setting, the idea is again that if the solution vanishes at a single point, then it has to be exactly 0. And both these maximum principles are established in this paper. And they play a fundamental role in the analysis. And also they play a fundamental role in establishing the mapping properties of our linear operators that we just defined above. It's important for us in order to, for instance, to generate the sequence of solutions in the monotone iteration scheme, we needed to find good mapping properties for the Poisson operator. And therefore, if in this setting, if we consider our operators that now also act on the boundary, we have the following properties. If the weight parameter here of these spaces is bounded by above and below, here is so that fields here decay at infinity, and we have a bound for below, from below, then the associated Poisson operator defines an isomorphism. And here, the proof is quite delicate and can be consulted in the lecture notes. The idea is that this condition here, bounding delta from above, put together with the maximum principle, it implies injectivity of the operator. This other condition here, together with a duality argument and the maximum principle, also implies the surjectivity of the operator. So this is how one proves this isomorphism. And then the operator associated with the momentum constraint with the conformal killing Laplacian is a Fredholm map whose kernel consists on the conformal killing fields of gamma. And in this case, if one adds a little bit of regularity, one can show that we don't have a kernel, that the S operator is also an isomorphism. This is done proving that this level of regularity excludes the possibility of conformal killing fields decaying at infinity. Again, all these proofs can be consulted in detail in the lecture notes, but the important thing is that we got good analytic properties that tell us when these operators are isomorphisms. And the claim that we were making about the non-existence of conformal killing fields vanishing at infinity under this regularity, it has been established under different assumptions in these three papers, for instance, and the kind of regularity that we are using is the one established in this paper by David Maxwell. Finally, let us comment on this next property. The idea is that we are going to need to analyze how the conformal factors behave near infinity. And the idea is to be able to prescribe the behavior of the conformal factors near infinity. And therefore, the idea is we are going to split our conformal factor into some function that we are denoting by omega, which captures the behavior of the conformal factor at infinity, and some function here, this curly phi, that decays at infinity. Okay? And therefore, omega has to be constructed so as to capture the behavior of our functions at infinity. In particular, it has to be able to construct to impose that omega approaches certain constants at infinity in each end, capturing the behavior of the conformal factor at infinity. This construction is extracted by this paper of Michael Holst and Caleb Meyer. And it's basically this lemma that says that if we have an asymptotic Euclidean manifold, and we have certain functions which are bounded on M, and their Laplacians belong to this LP delta minus 2 space, then there is a unique solution to this boundary value problem, where omega, the solution to this problem, tends to these prescribed functions asymptotically in each end as we go to infinity, and in particular, it is also trapped between the maximum and minimum values of these functions. And the idea of the proof here is, well, one starts with the prescribed functions and one uses cutoffs in order to extend them to the whole manifold. These cutoffs are taken so as to be equal to 1 near infinity, so as not to ruin the behavior of these functions near infinity. So omega 1 is asymptotic to these functions in each end near infinity. Then this condition on this hypothesis on the Laplacian of our prescribed functions tells us that the Laplacian of omega 1 is in LP delta minus 2, and also its boundary components satisfy this regularity condition. And therefore, one can use the isomorphism theorem that we just saw associated with the Laplace operator with Neumann boundary conditions to find a unique solution to this problem here. Okay, recall that the right-hand side here belongs to LP delta minus 2, so it is decays at infinity. So we can apply the isomorphism theorem, and therefore the difference of these two functions, this omega 2 that is the solution to this new boundary value problem, and omega 1, is going to be a harmonic function with homogeneous boundary conditions. Okay, and in particular, this is going to belong to this space here. So in particular, omega 2 is going to have the same asymptotic behavior as omega 1. This is what is important, that omega is going to have the same asymptotic behavior as omega 1. And therefore, omega is tending to our prescribed functions on each end as we move towards infinity. And so we have established existence for solutions to this problem. Uniqueness follows from the maximum principle. And then this argument proves the estimates. So the idea is that if we take epsilon to be below this minimum of all these functions, then since omega tends to these functions aj at infinity, sufficiently near infinity, the negative parts of this function is going to be zero. This is going to be compactly supported. And therefore, one can compute this L2 norm. And since on the support of V, the gradient of V and W are the same, one can compute this norm in this form. Then one integrates by parts and applies the boundary conditions on omega to find these identities. And then since this is zero by construction, one finds that this is zero. And therefore, this is constant and equal to zero because it has constant support, compact support. And this implies this kind of inequality for all epsilon that is below this quantity, and therefore we find the lower bound. A similar argument, but now using this form for epsilon and the negative part of this R function, proves the estimate from above. And now the idea is to use all these tools into the associated conformal problem for the Lichtenberg's equation. So now we have the Lichtenberg's equation with boundary conditions. This is similar to what we did in the closed case. We are denoting the right-hand sides here by f1 and f2. These intervals are taken so that these functions are smooth functions of y with bounded derivatives in y. So this is similar to what we did in the closed case. And all the coefficients are assumed to be in LP delta minus 2 or in this other functional space associated with the boundary with delta negative. So, and the idea here is that we need to use barriers. Again, the barriers are similar to our previous definition. So a sub-solution is going to be a W2P lock function that satisfies this inequality. And now we have a boundary inequality as well. And the super solution is going to have to satisfy the opposite inequality. With this, we have all the tools necessary for the monotone iteration scheme. And the idea then is that if we have an equation of this form with an asymptotic Euclidean metric, and if we have a compatible pair of sub and super solutions with this number L being positive, and these sub and super solutions are asymptotic to certain constants, satisfying this inequality. And we prescribe a function omega, just as in the above lemma, that captures the behavior of our conformal factor at infinity. So this function omega is asymptotic to certain constants that stay trapped between the constants of the barriers. Then our equation admits a solution that is between the barriers and that has the asymptotic behavior prescribed by omega. And the proof of this theorem runs in complete analogy to the previous one in the case of closed manifolds, but now one has to appeal to the techniques and the tools associated with asymptotic Euclidean manifolds and weighted spaces. So first one writes the conformal factor splits in this form here, and one constructs this sequence of solutions to linear problems appealing to the mapping properties now on weighted spaces. And one can start, for instance, with our subsolution. Then one appeals to the maximum principles in order to trap the barriers through an iteration scheme, through an inductive argument. And then one wants to apply elliptic estimates in order to show that this sequence is uniformly bounded in the correct spaces, these spaces. And here there are some subtleties related with the boundary coefficients. One needs to use certain extension properties and appeal to some sharp interpolation inequalities. This is all explained in the lecture notes. But once one has that result, then one gets this property of that the sequence is uniformly bounded. And therefore, one finished by applying certain function analytical arguments in order to extract conversions in the right spaces. And therefore, one proves the final claim of the theorem. And what is important now is to realize that we have once more reduced the analysis of the Lichtenberg's equation to that of finding appropriate variables for this equation. This is what we will do in the next lecture in order to complete the analysis of the vacuum case and asymptotic Euclidean manifolds. And therefore, we will now stop here and resume in the fourth